All right, well, since none of you have any questions, I'll just review something real quick with you guys, and it's on your Chem 101, and it's something Dr. Henry's gonna cover. So it's called bond order. I'm pretty sure you guys have seen it if you've done your Chem 101. And there are questions that ask you for what the bond order is. And to find the bond order of something, and it's just going to be a really quick review. Dr. Henry will go more in depth with it. So the bond order of something, or when they ask you to find the bond order of something, you do your bonding electrons. And then I'll show you what that means. So bonding electrons, and you're going to subtract that by your anti-bonding electrons. And then you're going to divide that by 2. So let's say that they ask, I'll do N2. So let's say that they ask you for the bond order of nitrogen gas. So what we're going to do, we're going to draw a molecular orbital diagram. And I'm pretty sure you've seen this you've seen this type of question in your Chem 101. So what we're going to do, we're going to take into consideration electron configuration of just nitrogen. And we know that it's 1s2, 2s2, and then let me look at my periodic table. And it goes all the way to 2p3. And when we're doing our molecular orbital, the only thing that we're going to take into consideration is the highest level. In this case, 2 is going to be your highest level. So we're not going to take into consideration that 1s2 when we're doing our molecular orbital diagram. So in some cases, I'm not sure if Dr. Henry wants you to memorize how to do the diagram. I would ask him. But in Chem 101, I saw that they actually give you the diagram. So let me draw it out. So it kind of looks like this: sigma 2s, and then these are 2s, 2s, and then you have your antibody one, which is sigma with that little star. That's still 2s. So it kind of looks like this. And then you have pi 2p. Then right here is sigma 2p. And then you have sigma 2p. This is pi. Let me redraw it again, like running out of space. So when we're drawing our molecular orbital diagram, the outside electrons are there to help us fill in the middle, because the middle part is what we're actually looking for here. So in this case, if we take into consideration how many, so we are working with N2, right? So we're going to split that molecule. On our left side, we're going to have 1 nitrogen, and on our right side, we're going to have another nitrogen. So here, if we take a look at how many electrons that second level holds, we have 2 plus 3. So that's a total of 5. So again, according to Hund's rule, we need to make sure that we fill it out each level first. So we're going to fill out the outside. So 1, 2, and then 3, 4, 5. And we have a second nitrogen. So it's the same thing: 1, 2, 3, 4, 5. And now what we want to do, we're going to count how many electrons we have on each level. So in this case, we have a total of 4 electrons, right? Counting this and this. So then we're going to fill in our middle part of it now. And again, Hund's rule, we need to go level by level. So 1, 2, 3, 4, right? And then here we have a total of 6, this plus this. And again, with our levels, we're going to count it 1, 2, 3, 4, 5, 6. Okay, so now the only thing that we want to take into consideration is this middle part now. So our bonding electrons are going to be our electrons that are not with our stars. Those are our bonding electrons. So these are our regular bonding electrons. So right here, if we count our bonding electrons, there's a total of 2, 4, 6, 8. So to count our bonding electrons, we have 8 minus our anti-bonding electrons are going to be our electrons with the little asterisk or with the star. In this case, we only have this one, so 2. And the equation says divide everything by 2. So we have 6, take away 2, would give us 3. So that would be the bonding order of N2. And you have a question like this, and this is how you're going to approach this question on your Chem 101. And another thing to note is that the higher the bond order is, the more stable this molecule is. So the higher bond order is, more stable. The lower, and vice versa, the lower the bond order is, the less stable the molecule is going to be. So if you have a bond order of 0, that's a very unstable molecule. In this case, it's 3, it's pretty high. So N2 is pretty stable. So it's just a little pre-review of what you guys are going to learn today, I hope.
Thank you for going over that.
You're welcome. Hey, Dr. Henry.
Hey, how's it going?
They're pretty quiet today, but I went over the molecular orbital diagram, or molecular orbital theory slightly. That's what they're going to learn today, right?
That's right. I thought you were going to go through the whole thing and tell me you're already done and everybody can
Oh
go
gosh. No. I gave them a little preview of today's lecture.
home. Okay, good.
Here, let me make you the host.
Okay.
Let's see. Oh, you're already host.
Oh, I take over once I come into the room. Man,
Yeah.
That's power. Ooh,
Yeah.
it's gonna go right to my head.
I don't mind the short meeting right now.
Let's see which class. Okay. Let's see. Okay. So at the beginning, we talked about, can you guys see my screen? Everybody can see my screen?
Yes.
So let's do some chit-chatting first, because I didn't get a chance to chit-chat with you. It makes me feel good when I get a chance to chit-chat with you a little bit. Okay, so how was the exam?
It was good.
Okay, good. Okay. So is Mauricio speaking for everyone? You guys all got together and you said, okay, today Mauricio is going to speak for us.
It was really good, and also the lab that we did that was due yesterday. I made slime.
You made slime. All right. Congratulations.
Yes. So
Don't you feel good?
yes, it's because I got very curious about, you know, putting the substance inside the glue with the DI water. So I did that and I got slime.
Yeah. Alex, what do you think? What do you think about the exam and making slime?
The slime was easy, and then the exam wasn't too bad. I expected a lot worse.
Wow. Okay. So I'm slacking. I need to get a little bit rough, huh?
No. I don't know. I didn't think it was too bad.
Okay. So that means you guys are getting more prepared. Yeah.
Mhm.
Taylor, what did you think?
It wasn't that bad.
Okay. Good. Good.
Dr. Henry, I have a question.
Yes.
So for, you know, one of the steps for the lab, it was asking to put color in the glue all together. So
Yeah.
since I didn't know what color to put, I just put Kool-Aid.
So you just put Kool-Aid in there. Did it work?
Yes, it worked.
So it's actually pretty good. So now you have one that smells and
Yes.
has color to it.
Yes,
Yeah.
I didn't know what to put, so I just put that.
Yeah, I guess the Kool-Aid packets come in handy for multiple things, right?
Oh, yes.
Good. That is really good. Okay, so now that we've kind of touched base, so at the beginning of this chapter, we were sitting there talking about how if we put magnets and we poured some liquid nitrogen in between, the liquid nitrogen would actually sit in suspension. It will sit right between the two magnets. And the reason why this is the case is because the molecule, the oxygen molecule, is actually paramagnetic. Paramagnetic basically means that it's going to be attracted to a magnet. Okay, that's kind of like for magnet. Para, para. For, isn't it? For in Spanish? P-A-R.
Yes, it is.
Yeah.
P-I-R-A. Yeah. So for magnet, right? Good way of remembering it. Maybe not. Where diamagnetic, something that's diamagnetic, it's all lined up. So it's not going to be attracted to the magnet. It's going to actually go through. Okay. So, and it's kind of, as I said, weakly repelled by the magnet. Okay. Okay. So molecular orbital theory is going to help us understand this process a little bit clearer. And so I'm going to kind of make an emphasis on that. So I'm giving you the pre part of it. And then you guys, just in case you may get a question like this on the exam. Okay, so at this point, you guys should be experts at valence bond theory, right? Valence bond theory is the concept of using the hybridization orbitals, right? It's using those pi, the sigma and the pi bonds. You guys remember sigma pi? When we're not talking about sororities or fraternities?
Yeah.
Yeah, okay, so help me out. Sigma. So when I say it's a sigma bond, what do I mean? If I say something forms a sigma bond.
They're bonded between either two s orbitals or an s and p orbital.
Okay, can I have two p orbitals?
No.
Are you
Oh,
sure?
yeah, they're
I
side by
can't.
side.
Ah, so if they're overlapping end to end, right? So like this. Right? So if it's in N, we can have bonding. Okay. So hybridization. What is hybridization? I know you guys all went over this with Jessica a few minutes ago, right?
No.
It's when
What
the
was that,
two
Mauricio?
orbitals
It's
combine and make it new shape.
so when we have orbitals that are going to be combining to make a new orbital, a hybrid orbital. It's like Dr. Frankenstein, right?
Yes, basically.
Okay. Okay, so molecular orbital theory is going to be a little bit different, right? So we're also going to be looking at sigma and pi bonds, but we're going to have what we call sigma bonding and sigma anti-bonding bonds. So we're going to have bonding and anti-bonding. And then I'll kind of get into what that bonding and anti-bonding means, okay? And the difference, one of the differences that are going to be between the valence bond theory is that we use molecular shape, or the EPG, to sit there and determine, you know, the number of regions of electron densities that are going to exist or are hybrid, right? So we use the shape to help us determine what hybrid we're going to need to make. So in this case, we're actually going to be predicting based upon electron arrangements, how it lines up in the energy shells. Okay, so that's going to be one of the major differences. Okay, although the other one is also dependent on energy as well, but we know that the hybrid was between the S and the P, so that energy level was lower than the P overall, but a little bit greater than the S. Okay. Okay, let's see. Okay, so you guys remember when we were talking about waves, right? And we said, so if a wave is in phase with each other, meaning that it has the same amplitude and the same frequency at the same component, so that wave is considered to be constructive, right? So here, these are two waves, they're in phase with each other, that's going to be constructive. Constructive basically means that you're going to get a greater amplitude, right? You're going to have the same frequency, but it's just your amplitude is going to increase. It's going to be the sum of both of those waves. So those waves come together to make a bigger wave, okay? So we also have what we call destructive interference, right? So it's destructive if your waves are out of phase, meaning that, you know, if you add the sum of them together, they're going to equal basically a flat line because they're out of phase with each other, so that they kind of subtract from each other. Okay, so one is like adding and one is like subtracting. So when we talk about bonding, bonding is going to be kind of like the same way. So our bonding is going to be when things are in phase. Our anti-bonding is going to be when things are out of phase. Okay, are you with me so far?
Yes.
Okay, now this is so much easier to understand when we're talking about dimers, right? Or in the case of homonuclear dimers, right? Or diatomic molecules, not dimers. Sorry, wrong class, thinking bio. Okay, so it's so much easier when we're sitting talking about the diatomic molecules. So, and we know a few diatomic molecules that we know that are going to be diatomic based upon what we know about chemistry at this point. And so we're going to spend a lot of time at looking at diatomics. However, this theory technically can work on things that are not diatomic, or can actually work on, okay? A little more complicated, but it can work in that regard, okay? So here's an example. If our, I'm gonna grab this. Okay, so if we have two s orbitals, right? So these guys are going to come together to form a sigma bond, right? Is that true?
Yes.
Okay, so now if we think about this, we have one electron in that one s orbital, and we have another electron in the other s orbital, right? So if these guys are in phase with each other, what we mean really by in phase is that we have electrons that are going in opposite directions. So when they come together, that we have a positive spin and a negative spin, and so they act as if they're one unit. So they'll come together as being in phase. In that situation, these guys are going to be additive, and you're going to get bonding. Okay. Now, if my electron is spinning one way, and then the other one comes in spinning the other way, so those guys are out of phase, right? So in that case, they're going to actually repel each other, and we're going to get antibonding. Does that make sense?
Basically like magnets.
Yeah. So like if they're positive and negative side of the magnet, it comes together, it sticks together. But if it's negative and negative, and you put those together, they repel each other, exactly like that. So does that make sense?
Yeah.
Okay, so that's going to be our premise, right? So the same thing is going to happen in this case. Okay, let me stop before I get ahead of myself. So the way that we signify bonding, the sigma bonding, so sigma bonding, we just put sigma, right? But if it's sigma star, that means antibonding. So that's how we depict antibonding. Okay, are you with me? Nobody jumped off the train yet? Okay, so when we're talking about, this actually works for the P as well too. So we could have a P sigma, right? Because two P's can form a sigma bond, and that's what you see up top here. So when the two orbitals are in phase together, meaning that in this case, we're going to use the color to kind of help us signify, meaning that the red and the red are close together, they can actually merge and then form a sigma bond, or a sigma px bond, okay? Where if it's out of phase, meaning that there's a blue next to that red, so they're not able to merge, meaning that they're kind of like going in the same way, right? Then we form an antibond. So they don't come together, they don't merge. Are you with me?
Yeah.
Okay,
Yes.
good.
Yes.
Okay, so when we talk about the pi, because a pi is just when we have two p orbitals right next to each other that are going to be able to merge, right? So if these guys are on opposite end, the colors are on opposite end, these guys are not going to come together and merge, right? They're going to be pushed apart. So then this guy is going to be pi star, which is our antibonding. Okay, but if the colors are right next to each other, then it's going to be able to merge, and then we're just going to end up with good. Yeah, no, maybe.
Yes.
Okay, good. See, clear. Okay, so now you guys are all worked up. You're good to go. Tell me what's going to happen here. So we have 3xp and 3xp. What's going to happen in this case?
They will come together.
They will come together and form a pi or sigma bond.
Sigma.
Okay, so we'd call it sigma, and then we write lowercase or subscript 3px. Okay, so it's a bond. So we're going to have bonding. They're in phase, they're going to bond. Okay, what about B? Come on, 50-50 chance. Is it bonding or it's not bonding?
Anti-bonding?
Yeah, this one is kind of really weird. It's not even near in phase, and it's not really out of phase. So you're not going to get any result at all, but it's going to consider it to be anti-bonding unless we get realignment. So we'd have to realign the orbitals. There won't be anything at all in this case. So nothing would result ultimately. Result. No result without realignment. Meaning that we'd have to get somebody in the same, they'd have to be both in the same, the X or the Y orbital. So we'd have to change the orbital that we're using. Okay, what about C?
Pi star. No.
That's right, pi star. Right? Because these guys are opposite colors, they won't be able to come together. So they're out of phase. We would get no, and it'd be 3py. Okay, piece of cake. Not too hard.
I have a question.
I may have an answer.
So the red and the blue, they just indicate different charges?
Not different charges. They're both the same charges, but it's spin.
The spin?
Yeah.
Okay.
Yeah.
All
So,
right.
and you want it to kind of, when it's in phase, that kind of means that you have one that's going one spin and one that's going the other spin. That's what it really means. So, and so they'd be able to merge if it's in phase. But if it's out of phase, it's not going to be able to merge. Do you understand?
Yeah.
Okay. Okay, so we have this guy here. So this guy is indicating what to us? Is this a pi bonding or sigma bonding or pi? That's right,
Sigma antibond?
sigma antibond. God, you guys are making this so easy. We're going to finish this in like 10 minutes. Okay. Okay, so this guy, he had spent a lot of time working on molecular orbital theory, and he actually used this concept of molecular orbital theory to kind of help him crystallize the HIV protease in combination with the drug. So the HIV protease was a very, very difficult molecule to crystallize. A lot of people were trying to use the valence bond theory in that concept of how much energy we need to add to kind of get that crystallization to occur. It never worked out. But Walter Cohen, he basically figured out that using this method, it allowed him to actually get it crystallized. But not only that, he was actually able to get one of the known drugs that was that inhibited HIV or HIV protease bound to it as well too. And so he actually went a step above and beyond in terms of crystallization. And it actually has made a huge impact in terms of drug therapy, and then also just in crystallization in general. So we want to give him his kudos. So let's see how the molecular orbital energy diagram is going to kind of look like. So here I have a case where I have beryllium 2+. Okay, so and then we're going to go back and do beryllium 2. Okay, so this guy is going to represent just the atom over here in the white. So that one is just going to be beryllium. This guy here is going to be beryllium plus. Okay, so meaning that it's lost one electron. Okay, so if we talk about the number of valence electrons, so beryllium has how many valence electrons?
2.
2. So we have both electrons represented here, one going up, one going down, opposite spins, right? because that's what we would do.
Yes.
Okay, and then here we have just that beryllium, which has lost 1 electron. So it just has 1 electron. So if we put these guys in, you take 1 from this guy, you put it in, you take 1 from that guy, you put it in. So that would be in your pi 2s bonding. Okay. And then we'd have 1 left over. We'd put that one in our pi star, or our antibond. So not pi, sigma. My head is, I'm sleeping here. So the sigma 2s antibond. Okay. So I'm going to teach you how to calculate bond length. I mean bond order, not bond length. Bond order. Bond order basically lets us know the strength of the bond that's going to form. It'll also let us know whether or not we're actually going to even have a bond. Okay, so bond order is going to equal the number of bonding electrons minus the number of antibonding electrons. Divided by 2. Okay, so I'm gonna have you guys do some really good math here. So if I have, how many bonding electrons do I have?
2.
How many antibonding electrons do I have?
1.
And we're going to divide that by 2. So we get 1/2. Okay, so if our bond order is 1, it's going to be 1 bond. If our bond order is 2, it's going to be, or single bond, I should say. If bond order is 2, it's going to be a double bond. If our bond order is 3, it's going to be a triple bond. And that's the most that we can have. It's a triple bond. Okay. Are you with me?
Yeah.
Okay. But we got a half. Have you heard of a half a bond? Anyone? No, right? So we know that that isn't going to exist. So we're not going to have a half a bond. So that won't work out. Okay. Okay, so that means that this guy is not probable to exist. Okay, so let's look at beryllium. So now we have Be over here, Be over here, and then this guy here in the middle is going to represent our molecule. So I'm going to save us some time. So if we take 1 from each one, we end up with bonding and anti-bonding. So how many bonding electrons do we have?
Four.
Do we have 4? Look in the middle. Bonding electrons. We don't take, so these guys are contributing to our molecule. We're only looking in the middle. So if, remember, this is sigma bonding. This is sigma anti-bonding. That's a star there, or sigma star. Okay, so how many electrons do we have here?
2.
2. So we have 2 bonding electrons, and how many do we have in our anti-bonding orbital?
2.
Okay, so 2 minus 2 divided by 2 is going to equal 2 minus 2 is what?
0.
0. Okay, so it's going to equal 0. So that tells us how many bonds we're going to have. How many? Gracia,
Yes.
how many bonds am I going to have? It's 0. So how many bonds does 0 equal?
Well, 0.
0. Okay, so this tells me that this molecule is unstable. It's not going to exist. Does that make sense?
Yes.
Okay,
So
you're
it won't
never-
connect?
Yeah, that's right. It's not going to bond, right? So if you get a bond order of 0, you're not going to get a bond. Does that make sense?
Yes.
Okay. Okay, so this is just telling you all of that we just talked about, right? So bond order, again, bonding, the number of bonding electrons minus the anti-bonding electrons divided by 2. If our bond order is 0, it's not going to form a bond. If our bond order is 1, it's going to be a single bond. If our bond order is 2, it's going to be a double bond. If our bond order is 3, it's going to be a triple bond. You good? Okay, let's go back. Let's go and look at hydrogen. Okay, hydrogen has how many valence electrons?
One.
Okay, so this represents our atom. This is going to represent our molecule. This is going to represent our atom. So each of the hydrogens are going to provide 1 electron. So if we get 1 electron from this hydrogen and we get 1 electron from this hydrogen, we're only in our bonding region. So how many bonding electrons do I have?
2.
How many anti-bonding electrons do I have?
0.
And then I divide that by 2.
1.
1. So how many bonds are between hydrogen and hydrogen?
1.
Does that work out for you?
Yeah.
Okay, so let's look at helium. Can helium form a diatomic molecule?
No.
Okay, well, you already got it figured out. You're ahead of the game. So yeah, if we look at our bonding, how many bonding do I have?
2.
How many anti-bonding?
2.
So 2 minus 2 divided by 2. Equals 0. How many bonds are we going to have?
0. None.
So it's not going to be stable enough to sit there and form a bond. Okay, does that make sense? Okay, good. Okay, so that's pretty much the meat and potatoes so far. So let me throw something at you to kind of make it a little more complicated. Okay, so here we have, these are the energy diagrams, and you'll notice that it keeps a certain pattern up until you get to oxygen and nitrogen, right? Between oxygen and nitrogen, it switches. Okay, so this is going to be kind of important, right? Because it'll help us understand that there are some distinctions. And remember, I kind of said this, and I said it a few times, oxygen and nitrogen, right? If you look at nitrogen, nitrogen is an exception a lot of times for different things, like electron affinity and what was the other thing? There's something else where we look at the trends and then nitrogen will pop up really high and then it'll drop back down for oxygen, right? And so it'll kind of screw up our little trend in that area. Find it. Give me 1 second. Come on. There we go. Okay, do you guys see P table there?
Yeah.
Electron affinity, I believe it is. Okay, so look at the electron affinity. So if we go across, it keeps going up, here, goes up, and then it drops way down, and then it goes back up. a little weirdo, right? A little oddball, okay? And you see, right? Here, it goes up, it goes up, it goes up, it goes way up, and it drops back down between nitrogen and oxygen, okay? And then it goes back up. Okay, so nitrogen is always this, it has these little quirks about it, okay? And if we look on this table here, let me see. These are our energy diagrams. We'll notice that between N2 and O2, we get switching of the sigma P and the pi bonds, okay? So in terms of energy levels. So at nitrogen, sigma is above the pi's, but at oxygen, sigma is below the pi's. You guys see that?
Yeah, I have a question, Dr. Henry. So what if you have a molecule like nitrogen monoxide? How would we draw the diagram in that case?
Okay, so one thing that we know about nitrogen monoxide, it does exist, but it's going to be an oddball because it has an odd number of electrons, right? And that's a good question, right? Because it's that energy level, it's between the two energies. So which one would you choose? So this is the one that is going to favor where we have sigma below the pi's. So if you guys remember, sigma below the pi, so that's going to favor the oxygen. This one is going to favor the nitrogen, right? So this will be our nitrogen type, and this will be our oxygen, right? So if we put it in here, so O and N, it's 3 and 1. I'm going to do the same thing for this guy.
And for the test, would they have to memorize how to draw the diagram, or will you provide the diagram for them?
Well, the thing you're going to memorize, because if you can take a look at it, so you're asking me in the case of the oxygen and nitrogen. Is that what you're asking me? So
Yes.
Between the two? That's a good
Yeah.
question. I have to think about that. So they should know that there is a difference between the two, right? They should recognize the difference between the two. And that's going to be important. But
Okay.
I haven't decided whether or not. I have to think about it. Give me some thought. But if you look at it, right, the bond order is going to be exactly the same under these circumstances because it fills in all of the bonding ones, and then you're just left with one antibody. So ultimately, grand scheme of things, it's not going to make a difference in this regard. Does that make sense?
Okay, yeah, that makes sense.
Okay, so in this situation, it's not going to make a difference. But in other situations, it can. So in the case of, let me show you the whole thing with the O2 because this is the meat and potatoes. So in the case of where we have oxygen and oxygen, and we're forming O2, and then we'll do the same thing with nitrogen. Nitrogen over here. Oops. Okay, so under these circumstances, right, then this guy is going to have 2 electrons that are free to interact with the magnet, right? So remember, paramagnetic. And then under this case, for the N2, this guy is not going to have anything free to interact with the magnet. So this one is going to be diamagnetic. Oops. Okay, so what is the bonding order for oxygen? How many bonding electrons do I have?
E.
You said 8. And how many anti-bonding electrons do I have? That's a star there. Remember, the star represents anti-bonding. I heard somebody say it under their breath. Somebody said 4. So 8 minus 4 divided by 2.
2.
2. And we know that oxygen has a double bond between it, right? Holds up so far? Okay, what about nitrogen? How many bonding electrons?
I'm kind of confused on how to like read that. How do you get
So
that?
if it doesn't have, so you want to look at the center one right here
Mhm.
in the middle where that gray's at. So if it doesn't have a star on it, those are bonded. If it has a star on it, and usually the star is going to be higher energy. So if you think about it, if it's repulsing each other, that's going to be more energy. So you're trying to put something that really doesn't want to be together, right? So it's going to take a lot more energy to kind of keep that together. Does that make sense? So those are always going to be higher in energy. So your anti-bonding is going to be higher than your bonding. So how many bonding electrons do you guys see here? Down here at would be the S orbital part of it.
Just that one.
Just that one. So that's 2. And then these are also bonding. So we'd add that up with this.
So 6.
So that's 6. 6 plus 2. 6 plus 2 is 8. Minus,
Okay.
and this is our antibond.
The 4 or no 2?
No, just the 2. Okay, so remember, the middle represents the molecule. The ends, these guys are they're feeding to the molecule. So these are that's one of the ends. This is the other end. And then these are all of the valence electrons, right?
Yeah.
All the valence
You don't
electrons.
add on top?
What was that?
You don't add those 2 anti-bonds on top?
There's nothing in them.
Those right there? Oh, okay.
Yeah, so these guys are empty, right? So these are all bonding. So we have, these are pi's. These are just regular pi. Pi. And then it's sigma. And then up here, these are pi anti-bonding, sigma anti-bonding. Do you see that? Okay. So we only have 2 anti-bonding. We have, these are bonding, all of these are bonding. So that's 2, 4, 6, 8 bonding minus 2 anti-bonding. We divide that by 2, 3. So that means that we are going to form a triple bond. Do you guys get that?
Yeah.
Okay, so before we go, we're almost done here. Oops. Okay, what about fluorine? So if we have fluorine here, so if this was F, and we're making F2 in the middle, how many valence electrons does fluorine have?
7.
It has 7. So that's 1, 2, 3, 4, 5, 6. Let me add one more. 7. Okay. This guy has 7. So when I fill this in, then these guys. Okay. So is it paramagnetic or is it diamagnetic? Mauricio.
Yes, I'm here.
Did you say dia?
Yes, it's dia.
It's
For fluorine,
diamagnetic,
correct?
right? Because these guys, the molecule is all paired up. There's no loose electrons. So in this case, it's paired up. So if we were working with fluorine alone, but not fluorine the molecule, right? That guy would be paramagnetic because you have that one electron by itself. But as a molecule, when it's together, F2, it's diamagnetic. Okay, so is that going to work? Is it going to really bond? Is F2 going to bond? So the way we calculate it is, it's our bonding. How many bonding electrons do I have? Alberto, how many bonding electrons?
I'm not sure.
So remember the thing that has the asterisk on it?
Yeah.
That means it's anti-bonding. If it doesn't have an asterisk on it, and we're only looking at the center here, right? Because this is our molecule. This here represents the atom. Somebody said something in chat. Okay, so Mauricio says that there's 8. So there's 8 bonding. It's 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bonding. And then we subtract the anti-bonding. The anti-bonding is the one that has a star. So how many stars do we have? How many electrons that have
6.
stars on them? 6. Okay, and we divide that by 2. So we have 8 minus 2 divided by 2.
1.
Okay, so that means that there's going to be one bond between each of the fluorines. Okay, simple.
Yes, kind of.
Yes, kind of. Okay. Okay, so now I'm gonna give a leap of faith. Okay, here. Okay, so when we're talking about insulators, right? So things that don't conduct. So the way it kind of works is that this whole concept of molecular orbitals in terms of solids, if the energy gap between our valence and our conduction is huge, it's going to be an insulator. So basically, these are valence electrons. And if we have a gap between our conduction and our energy so that these electrons can't be pushed up, right? It takes a lot of energy to push them up. That is going to serve as an insulator, right? If the gap is not as far away between the two, right, then it's going to be a semiconductor. So with a little bit of energy, it's going to be able to be pushed up and it's going to be able to conduct. With conductors, these guys, there's no gap. So there's no energy gap. So the electrons are able to flow into that conduction level. Okay. So Are you with
Yeah.
me? Okay. So in terms of that energy, right? That gap between energies. So if we go back to this represents that energy. If there's a gap between when we're making our molecule, big enough gap to kind of push it in terms of to that other level, when we're bringing everything together, then we're gonna have an insulator. It's not gonna be able to conduct anything. But if the gap is medium, then we can be a semiconductor. So we have to put energy in to get it to conduct. And then in the case of there's no gap between it, then it's going to conduct readily. Okay. Okay, so my last slide. So remember we were talking about oxygen. We already showed this already, right? So here's a kind of a better picture so you guys can take a look. But this here represents each oxygen atom. Valence electrons. How many valence electrons does oxygen have?
6.
6. 1, 2, 3, 4, 5, 6. Okay. This has the same. 1, 2, 3, 4, 5, 6. So literally all we're doing is we're taking one electron from here, we're putting it in the lower energy level. We're taking one electron here, we're putting that in the lower energy level. Take the next electron, we're putting it here, we're putting it in here. That accounts for all 4 of those electrons that are in between both of those oxygens. Here we have the other 4 electrons. So we're going to do the same thing. This is lower in energy level. So then you fill these guys up from the bottom up to the top, and we recognize that we end up in our antibond. Okay. So if we calculated our bonding order, it's going to be bonding. How many bonding do I have?
8.
8.
Okay. And how many antibonding?
2.
8 minus 2, are you sure? Only 2? Because that's 2 here, but what about this antibonding down here? You see it at the bottom? You have the 2
Yeah.
here, here, and then you have the 2 here, so we have 4. So 8 minus 4 divided by 2.
2. Right? Oh.
That's right, 2. And that's what we expect. It should be a double bond between oxygen, right? Okay. And we know this guy has 2, the molecule has 2 unpaired electrons. So we know that when we put it between a magnet, it's going to be paramagnetic. It's going to suspend. Did fluorine suspend? You guys remember? Or was it? No, we already calculated that because Mauricio says it was diamagnetic. Okay, questions, concerns, Cash? Cookies? Cake? Okay, that's all I got for you. So have a good break. Oh, wait, that isn't true. Fine. So tomorrow at noon, there is going to be a Women's History Month event. You guys could get extra credit if you guys attend and take a snapshot and upload it. The link is in modules under events. So make sure you guys come and get that extra credit because it may help you get that, instead of getting just that A, you may get a super A. A++, So. Okay. And then next week is spring break. So if anything pops up, ignore it because you guys are not supposed to do any work from chemistry for spring break. You may get an email or something like that. Pretty much ignore it because I'm probably not going to send it out to the very last minute in the first place. So, but it's next week is spring break. Don't expect to see you guys here. I'm not going to be here. So take advantage of it, get some relaxing time because when we get back, we're going to be going into 4th gear. Okay. I need your brains. I need that energy. And I need you guys to be interactive. Come back with a new attitude and we're going to be turning it up, right? we'll do shots of energy. Okay?
Okay.
Okay. So you guys have a good weekend. Enjoy your break. I'll see you guys in either tomorrow or a week and a half.